for the organizers for first organizing this and then reorganizing this and then reorganizing this and kind of sticking with it so that this has all worked out so nicely. So far, I've really enjoyed my time. I want to try to start a little bit at the beginning. I mean, it's a little too much to do all at once. So I'm going to emphasize more thinking about questions about when we have unique ergodicity and what goes into those ideas. And I'm sorry, my title was intended to kind of imply that I'm going to give details sometimes, but I'm going to more emphasize kind of how I think about it and some issues there and try to let you think about that. And I'm also going to try to bring up some open questions here and there per the instructions. So here's an SDE, and by that maybe I mean an SODE or an SPDE. That's an E missing. Right. So I have some equation here, right? This is of course just notation for this integral equation. So I have some collection of Brownian motions. So K Brownian motions. I mean, so some collection, maybe infinite collection of Brownian motions. And each of these I usually tend to write these as one-dimensional standard Brownian motions, or maybe complex standard Brownian motions that are forcing in some direction in the function space, all right? Typically, I'm just going to write the state space as kind of some large X. When it's important, I'll try to bring up exactly what I'm talking about. So if you have this SD, if you have this stochastic equation, so for every omega and every initial condition, you get some path, or almost every. And you can define a semigroup. So this P, which acts on functions or observables, you might say. And it's the expected value of this function evaluated at the random time xt. So I apologize for all the experts in the room, and it's kind of a mixed crew here. So I'm trying to just make sure everyone's on the same page. But you can object at t politely to me in between if I'm going too slow in your opinion, if I'm going too fast. So here we have this Markov semigroup acting on functions. And we can also, there's an adjoint to that, which you might write P star, but actually I prefer to write action with measures. So that's the initial data. So it starts on the left. A well-known probabilist made me promise for 1 month to write things this way. And she promised me when it was all over, I would never go back. And she was correct. It makes sense if you think about matrices too. These are row vectors and these are column vectors. And this is a matrix. Everything is just much nicer. All right, so if you take a measure, so this is taking the initial data and you push it forward PT and you get a new measure. So if you want to see what that is, that's just saying I'm going to evaluate the probability of ending up in A starting in X, where the X is distributed according to this initial probability measure, right? So that's how you push measures forward in time, right? An invariant measure, Markov setting equivalently a stationary measure, would be a measure which is a fixed point of this semigroup. I say when you start with that random initial data and you go forward some amount of time t, you end up with the same measure. Okay. Sometimes, since so I should also say I'm not trying to give the most general theorems. I'm not at all going to generally think about rates today, tomorrow, or the next day. I'm just going to think about kind of what you need to think about to even have a unique invariant measure. Rates are really important, but I'm purposely choosing to focus kind of at one set of questions, which I think highlight fundamentally the difference between SODEs and SPDEs. That's kind of the theme of what I want to talk about. I want to highlight what are the issues there. All right, so you can also take this initial data and think of it as initial data at time 0. And then, let's see, by the way, where's the chalk? Chalk over here. You can also take this as initial data at time 0, and then using that, you can flow forward to a finite set of times, T1, T2, T3, they're increasing. And that set of finite dimensional distributions are compatible in the sense of Kolmogorov extension theorem. So that defines a measure on path from 0 to plus infinity, right? And I'll write that this way. So this is the measure that's induced by starting with this measure at time 0 and then flowing forward in path space. So this is a measure on path space, right? Okay, and so this is on X with this time script here, right? And that's the paths, right? And so sometimes it'll be useful to think that way. This is kind of a canonical way. This is a lifting. This is a canonical way to take a Markov process and lift it up to an object in path space. And when you do that, then you change your dynamics into just the shift dynamics. That's to say, to move forward in time, all you do is, this is like a tape that has all the future in front of it, and you just shift it back and chop off the part that's stuck over 0, yeah? And so you just change your origin. So this map just shifts a path by S, okay? So then if mu was an invariant measure for PT, then this measure, which is now on one side of infinite paths, and I could have done two-sided infinite paths. There's no real reason not to. I just chose to do this. Well, there are reasons to, but there are choices, and all choices have consequences. So I made this set of choices. Choices have consequences. With knowledge comes responsibility. I'm starting to sound like one of those people. That's really creepy. Then this measure on path space is now an invariant measure for the shift operator, right? Because it's just kind of it's obvious in the true sense of the mathematical sense of obvious. It doesn't make sense until you understand it, and once you understand it, you don't understand why no one else doesn't understand it. So you're starting at time 0, right? And then you shift to time t, but it's an invariant measure, so the distribution at time t is still mu. So then it's just like as if you started at time t and then went forward from there. And it's the same thing after you shift it back, okay? So it's an invariant measure. Please interrupt me. There's no point in me doing this if no one interrupts me. Alternatively, my advisor was Russian, and I get uncomfortable if I talk for too long without someone interrupting me. I preferred if no one actually came and took the chalk out of my hand and started writing on the board. But if you need to, please feel free to. I forgot this is being recorded. Oops. All right. Sorry, I've been making that joke for decades. All right, the set of invariant measures is convex. It's a convex set, either whether I'm picking on path space or in the Markovian setting. So that is to say, if I take two different invariant measures and I pick a number between 0 and 1, and I make this convex combination here, right? That is invariant. It's rather straightforward. You just act on it like this, and you get this because it's invariant, right? That gives that. Whoops, sorry, wrong one. That gives that, and that gives that, yeah. And then that was just the definition of mu alpha, okay? So it's a convex set, which is nice. And any convex set has some notion of extremal. So extremal measures are exactly the measures for which you can't write it as a convex combination of two different other measures, right? And in convex geometry, the extremal points are in some sense like a basis, right? They're the things by which all other things can be written as linear combinations, as convex combinations, right? So that makes sense that some of those points should be important. And I prefer to introduce it in this way. It's usually often introduced in the opposite direction, but I think the extremal property is as important as anything. So these extremal points in this convex sets have a special name. They're called the ergodic invariant measures. And so now let me explain why they're called the ergodic invariant measures. So yeah, please. Yeah, please, thank you. You can always count on old friends, please.
Why is it convex?
What? Oh, why is it convex?
I mean, you could do that for any alpha, right? You could take the sum of any invariant measure.
Well, because I want to have mass 1.
Okay.
So that I meant to say yes, thank you. So there are a couple ticks in there are abuses of language that different communities make. So in my world, I'm almost always thinking about probability measures. So they're always normalized to be 1, right? It's perfectly reasonable. There are times when you might care about unnormalized, that's just sigma finite invariant measures. I'm not going to talk about that today. Equally, I meant to say this at the very beginning. So when probabilists say invariant ergodicity, actually, what they really mean is unique ergodicity. That is to say, there's a unique invariant measure. And the reason that is that when dynamicists talk about ergodicity, they specify, and they mean something different than unique ergodicities, because in probability theory, it's very unusual for things to have more than one invariant measure. And in dynamics, it's very usual for things to only have one invariant measure. So you kind of...
I think you said it backwards.
Okay, well then the other thing. In probability, it's very likely when you have noise in a system that there's only one invariant measure.
A nice way to say it, John, is that in deterministic ergodic theory, there are way too many invariant measures. There are just way too many.
Way too many is a personal preference. So
ask me if you want to know.
okay, I do know, but anyway, yes, thank you.
Not the only one.
All right, so the ergodic decomposition is written as a convex combination. So the ergodic decomposition then says that you can write these measures in the interior as a convex combination measures, which are these extremal points, right? That's what the invariant measures. That's what the ergodic becomes. Of course, I've written it like a polytope here. It could have curved edges, right? A circle, every point is a convex, is an extremal point. If you have a circle, if you have a curve. So, and this is like an infinite dimensional object, as Alex correctly says. I mean, this is like a horrible object in many settings. So it's not so, I mean, sometimes it's not infinite dimensional, but sometimes it's horrible. So this ergodic decomposition says that you can actually only study the ergodic measures because every other measure can be written as a convex combination. So you might as well study the extremals. All right. So extremal invariant measures equals ergodic invariant measures.
Can you just scroll up so we can see the end of the theorem?
Extremal invariant measures are the same as ergodic invariant measures. And let me just maybe say a little bit more about that. So let me give you what's the more classical definition of an ergodic invariant measure. So I'm going to give you two different versions in the Markov setting. So before I define ergodic invariant measures, I'd like to think of them as extremal measures. But let me now go ahead and kind of give the more classical definition. So I need to define what an invariant function is. So an invariant function, if I think about it just in the Markov setting, it's just a function that when I apply the semigroup to it, I get the same function back, mu almost surely. So when I'm talking about an invariant function, I'm talking about an invariant function relative to a particular invariant measure. So here my invariant measure is mu. So that's true. Or alternatively, on path space, it's a function so that when I shift it, I get the same function back almost surely. Statement, what an ergodic invariant measure is, an ergodic invariant measure is a measure such that every invariant function is almost surely constant. And that comes up, that's going to somehow jive. It's a pure state, right? Whenever I do something with respect to this, I only get one number out. I get one answer out. So in particular, the place that comes up, the best place to talk about that. Oh, before I do that, I just have this little diagram, which I'm not going to prove all of this, but it's actually one arrow in here is hard. There's actually two arrows in here that are hard, and you can choose to prove one of them or the other, and then all the easy arrows finish the diagram. But I'll just say that just if you're wondering, if you're in this Markovian setting, ergodic is equivalent to extremal. And if it's ergodic in the Markovian setting, that's the same as when you lift it up to the path space, it's ergodic. And if you have a measure in the path space, which is ergodic, which is obtained by pushing something forward, that's the same as saying it was ergodic down the base space. If it's same thing, if it's extremal here, it's extremal there. So that's this whole thing's equivalent, all right? And probably the kind of the workhorse in many ways, there are a couple workhorses, but this is the first. If you only know one, you should know this one. This is the Burkhoff ergodic theorem, right? We've already had a little bit of talk about this. Scott discussed this at least for a little while in his talks. Let me just kind of state this. So if we have an invariant measure, which is invariant here or invariant here, and then if I take a function, an observable f, which is L1, so in particular, a bounded function is fine. That's what people often take first. And then if the theorem says two things. First of all, this time average exists. That's non-trivial. That's an important statement. This time average exists, mu almost surely. All right. And then this function is an invariant function itself. And it has this property, which is if you average against f bar, it's the same as just averaging the original function against mu. And so if it's invariant, that says that if this invariant measure mu was ergodic, that means it's almost surely constant. And now we finally arrive at the place where I first heard about the ergodic theorem, was like in my stat mech class, right? It was that ensemble averages equal time averages, right? And so here we have some time average equals this ensemble average almost surely, because it's just constant. And we want to object or ask questions.
Checks out, John. Looks good.
Thanks. Okay. All right. So, of course, if you have this path perspective, up here, I wrote it as x to t. I could have just easily written it as this object drawn on path space and then looking at the shift of it under theta. And I could have even had a function here that depended on the whole path that was L1. It didn't have to be just at a time t. So that's not so important for our discussions. All right. All right, so this is important. So now just to kind of drive this home, I'm going to just give two consequences. I'm going to give one theorem, which is a kind of a structural theorem. And I actually, against my better judgment, decided to give you some of the proof here. And why? Because I think the ideas are the same ideas that come up later. And so I thought this would, if the more times you see if an idea used, it kind of sinks in. So I want to use it in the simplest case first and then use it again and again and again. All right, so let me just make some statements. So if M and mu are invariant measures, then the following statements are true. If M is ergodic, it's absolutely continuous with respect to M. What does that mean? Remember what that means? That means that whenever M makes a set, gives a set measure 0, so does nu. Yeah? And that sounds like a trivial statement, but it's very deep. It has a lot of. That implies actually that M equals. Secondly, if these are both ergodic, then either they're the same measure or they're singular. And what singular means is that you can find a set of measure 1 that M gives that set measure 1, and you can find a disjoint set like the complement for which nu gives measure 1. Right? And that's how really kind of justifies my discussion of these ergodic measures being the extremal points, right? And being a basis, right? We think of a function, things being a basis if they somehow represent different directions, pure directions, right? And the things that other points in your space are linear combinations of the basis elements. Well, if each of these measures are singular, one with respect to another, they really are disjoint. They're the only measure in town that can bring that set of typical points to the conversation, right? Right. So one thing to think about. So here's like, if you think about like a Hamiltonian system, and let's just, say so I'm putting a Gibbs measure on that, like e to the minus x to the 4th minus x squared, right? That's a double L potential. And you can think there's all these orbits. I think about the second order dynamics, right? So the Langevin or just with momentum. There's all these orbits that are level sets of that Hamiltonian, right? That I'm whizzing around. And every one of those orbits is its own, the occupation measure, how much time it spends as it whizzes around that orbit on each point is an invariant measure. And each of those is ergodic. Of course, e to the Hamiltonian is also an invariant measure, but it's actually made up of this infinitely many ergodic invariant measures, right? It's a convex combination. These are the level measures on these level sets, right? And then it's a mixture of those with some weight, right? So that's exactly the kind of thing you have to think about. What happens in a stochastic process often is because we inject this randomness, we set things up so that there's only one invariant measure. And that's why people do it often, right? Because it brings us from a setting where we have many, many invariant measures to a setting where we might have only one. Right, so you can go see this in many, many places. One example is Cornfield, Frohman, and Sinai. For reasons that have many reasons, that's my place I always go to for much of this. All right, so let me just prove this. So I'm going to prove the first statement quickly, and then I'm going to prove the second statement. All right, so what's the first statement says? That if M is ergodic and mu is absolutely continuous with respect to M, then they're the same measure. All right. So if M is ergodic, there exists a measurable set and A is a measurable set, then for almost every initial condition, for M almost every initial condition, the Burkhoff's ergodic theorem says that this is true. This limit converges, and it converges almost surely to a constant because the measure is ergodic. And that measure is, when I average this against the invariant measure, which averaging the indicator function against the measure just gives the measure of the set. Everyone agree? Now, since this is absolutely continuous, dominated convergence, this is like the original bounded function, right? The indicator function, right? So I can just take this integral here and integrate both sides, yeah? And if I integrate both sides, this is a constant, so it moves outside, and I just get that because this was a probability measure, yeah? And now when I integrate this, I then observe, hey, this was an invariant measure. So this is just pushing forward by time s. So this thing is, at every single time, this is just nu of A. So I'm integrating nu of A, which is constant from 0 to time n, and then dividing by 1 over n, so I get nu of A. And so now I've just showed that nu of A equals nu of A. So the two measures are the same because A was an arbitrary measurable set. Yeah? Burkhoff's ergodic theorem. Magic.
Can you slow down slightly and point out how dominated convergence was used?
Yeah, I'll have to think for a second. Let's see. So I haven't thought about that for a while. So let's see. You want to integrate on the outside of this limit, and then say that's the same as bringing it inside, right? And so you just needed that was an integrable function with respect to this, and it was for all A because it was just invariant. You want to bring the integral outside and bring it inside the integral. That's what dominated convergence lets you do, right?
And where is the new absolutely continuous with respect to m showing up?
Because the fact that this integral, since it's on a set of measure 1 for new, this integral is equal to ma on each slice, like Fubini.
Okay.
So therefore, this is true. Yeah, does that help?
I think so.
Yeah. Come ask me later.
Okay.
Here, this one's even more relevant for us. This, which seems like this fantastical property that ergodic measures are singular one with respect to another, is again just a consequence of the Burkhoff's ergodic theorem. So let me do that. So two, here we go. So we want to show that these two measures are either singular or they're identical, right? So let's assume that they're not identical and show that they must be singular. Yeah, that's enough. Yeah, everyone agree? All right, so if they're not identical, there has to be a set where they don't agree, a measurable set where they don't agree. Everyone? Yeah. All right, so now let's define a sub m and a sub nu as the initial condition so that when I integrate along them, I converge to this value and this value. I can just make that definition. Burkhoff then says that these are each measure 1 sets with respect to this measure. Burkhoff says that these are not empty sets, and in fact, they are measure 1. By construction, these sets have 0 intersection because you can't converge to this number and converge to this number, which is different simultaneously. You're like, where did that? Burkhoff, it's magic. Similarly straightforward is the statement about convex. It's just another argument like this, using invariance and Burkhoff's ergodic. Okay, 2 is enough. All right. Does that make sense? I mean, let me just say this again, right? The fact that these sets are sets of full measure for these two measures is just a part of Burkhoff, right? There is a set of full measure of C so that this system converges and converges to these numbers, all right? Okay, great. All right, so let's go back to this setting for a second. So now I want to kind of talk about this very simple setting, which I'm going to come back to a few times in my conversations. I want to give you a first, yeah, please.
Sorry, this is a very silly question, but is there supposed to be a plus assuming that DT?
Oh yeah, absolutely. The amazing thing is I usually leave out the DT and put in the plus. My co-authors are laughing. All right, so so this is an Ornstein-Uhlenbeck process in 1 dimension, yeah. And so it has its transition semigroup can be just written. So this is a P with a little bar on the bottom. See that? And this is a P with no bar on the bottom. That's the density, yeah. And so this is just a Gaussian density, which I've written here. You can see that 100 different ways, but just if you've never seen it before, just take it as true. Now what I want to do is I want to compare the densities starting from 2 different points, x and x tilde, yeah? And I'm just going to use this trivial identity, which is kind of actually rather important indeed, and source of many proofs of many different statements. So first, I'm going to take, these are 2 positive numbers, or non-negative numbers. They're positive in this case, but general densities are non-negative. So I'm going to take the min of them, that's probabilist mins. And then I'm going to take the difference of them and do plus. I claim that's an identity. Then I'm going to do min again, and then I notice here I reverse the order. I'm going to walk back in a second. How do I change it when I go back?
Oh, no, it's okay. You can see it all the time.
Okay. Makes me very small. So, all right. So then we have this statement, all right? And the point, what's interesting about that is, so what you should really be thinking is this is the common part of the probability measure, and this is the disjoint part, because these two things are positive actually have singular disjoint. If this is positive in y, this is 0 in y at a point y. If this is positive at a point y, this is 0 at a point y. So these are densities of disjoint measures. If you now said, what's the L1 distance between these two? Hi, Luigi, what's up? It really isn't zooming out because the screen is too small for us to really tell what's the, got it, Luigi. That's really convenient. It goes like, hey, Monsieur à tout le monde. All right. All right. Sorry, don't get upset. All right, so here we have alpha, which is the difference, the L1 difference, 1/2 the L1 distance, and I'm a probabilist, so I always divide by 1/2 here. 1 is a special number, 2 is not. So it's better to have it normalized to be 1. We can talk. All theorems are beautiful when you make it divide by this 1/2, basically. And so that is the total variation distance between these two measures. All right. And one thing to notice is actually equal to, right, that's actually equal to, without the 1/2, the plus part here or the plus part here, which is just a fact you can verify. If you don't know how to see that, I can tell you that afterwards. And now let me make a point. This transition density now can be written. So that's this. See, I'm starting with a delta measure at x and I'm pushing it forward, right? That's just a more compact notation. So now I take this density that I wrote here and I just normalize it by, this one is normalized, the total mass here is 1 minus alpha and the total mass here is alpha. So I normalize this by 1 minus alpha to make it a probability measure, and then I have to multiply by 1 minus alpha. This I normalize by alpha and multiply by alpha. So this is now the actual probability measure. That's what I mean by this notation. And what's interesting now is you can really think of this as a mixture. Taking a step with this Markov chain is first flipping a coin that comes up heads with probability 1 minus alpha and tail with probability alpha. And if it comes up heads, I choose from this measure. And if it comes up tails, I choose from that measure. Yeah. And what that does is it lets you think of a coupling. So it says, if I want to build these two Markov chains starting from here and here, might not have had any intrinsic correlation. They were just two copies of the Markov chain, but I can build them in a correlated way so that that's useful to me. So what I can do is whenever it comes up heads, I can actually draw from the exact same measure. And what that means with probability 1 minus alpha, I actually move to the exact same point, even though I started at x and I started at x tilde. So what we've seen already here is somehow the fact that these measures are not singular, time t, lets us build a construction which makes the fact that the system forgets its initial condition. It no longer knows whether it was at x or x tilde from before. That information is gone, right? So it forgets that, and that's what ergodicity is about. Ergodicity is about the forgetting of the past, right? Because the long-term behavior becomes independent of how you started exactly when the long-term behavior forgets where it started. For all the philosophical blah blah, but that's what the title, you should have been ready for it when you read the title. All right, so then two different ways of saying that is that you can actually say that this is the infimum overall coupling. So a coupling is just a measure on the product space where the first marginal is this measure and the second marginal is that measure. All right, so this lets you build a coupling so that coupling gamma is what I'm calling it, so that the probability of them not being equal is exactly equal to the total variation distance. So the total variation distance is a number between 0 and 1, because I'm a probabilist, so I normalized it by 1/2, so it's not by 2. Which is nice because now it's a probability. That's one of the main reasons. So now it's a probability. So that's exactly if I try to make two random variables agree as much as possible, then the probability that they don't agree is exactly equal to the total variation distance. Okay, so I had this little picture here because I actually drew a whole bunch. You can actually see in here the purple, the pink, which is the min below them. So it just shows how if you have two density functions, as a general fact, you can decompose them into this min part and this plus and minus part, and you can define they don't have to have a density with respect to Lebesgue. You get the same construction works in absolute generality in Markovs in any measure space. All right, so here's the point what we just saw, was that since this total variation distance was less than 1, that means there existed a coupling gamma, x1, so that the probability that they were equal at time 1 was positive. So there's some chance that if I start at x and x tilde at time t, I can construct copies of these two processes so they're exactly equal at time t. And of course, now they're Markov processes. So if they're equal at time t, what they do from then on can be made to be equal. So in fact, there exists a coupling of the entire future of these processes, right? So that's the future from 0 to infinity, 0 to infinity, yeah? so that the probability that they're equal for all times s greater than t is positive. I see, he's locked out. Yeah. All right, so what's the consequence of that? So if I'm giving two ergodic, so what do I want to do right now? I want to show you that this is enough to conclude that there's only one ergodic invariant measure. At time t, knowing that the time t marginals are not singular with respect to any 2 points x and y, I don't care about how not singular, just not singular, right? That's enough to show that there's a unique invariant measure. All right, so let's just do that. And this is not the quickest proof. This is a proof I'm choosing for philosophical and conceptualization reasons that will be useful for what comes next, okay? So I'm not claiming like, oh my God, there's such a clear proof. You could have just written this one thing and it would have been done. That's correct. You're correct. All right, so let's write this out. Let's take these two invariant measures, which are both ergodic. Let's define gamma nu tilde on the product space, on the infinite paths, as just the measure that I defined above for x and x tilde, but now I integrate it over these two different initial conditions, right? So at time 0, this is a delta measure at x in one coordinate and a delta measure at x tilde in the other coordinate, right? So when I integrate them over these two measures, I actually end up with a coupling that at time 0 looks like nu in one coordinate and time 0 looks like nu tilde in the other coordinate, yeah? These measures have the property that at time t, there's a positive chance that they are equal for all time after t, yeah? So the chance that this one is equal after time t is positive also, because it's just the integral of this positive number over these two probability measures, right? So it has to also be positive, yeah? So this is true. In particular, I now could invoke Burkhoff. I can say, you give me a test function, whatever your favorite test function is, you pull it out and say, hey, I don't believe these two measures are different. Why don't you check this function? And you think you got me. And then I say, okay, fine. Then I'm going to say, okay, let's take that function. Let's integrate against one of your ergodic invariant measures. Burkhoff says that there's a set of measure 1 so that these paths converge to this, yeah? And Burkhoff also says that there's a set of measure 1 where these paths converge to this, right? So I can intersect. So when I intersect those two sets of measure 1 with a positive probability, I have to be left with a positive probability. So there's actually, under this coupling, there's a set of paths so that the x path converges to this number, the x tilde path converges to this number, but we know that after time t, they're identical. So they both converge to the same number when I time average along them. Yeah. So the picture is this, right? The picture is this. So here I'm starting at a point which is distributed according to nu. It's random. And here I'm starting at a point which is distributed nu tilde. And I built this so that after time t, there's a positive chance that for every point that I choose here, there's a positive chance that they agree. Show that with probability 1, this path had to converge to integral phi d nu tilde dx. And these paths had to converge to phi nu dx, yeah? But because they agree after time t, they have to converge to the same thing, yeah? How am I doing, David? All right, I'm all right. 10 minutes, is that right? So David check his watch. He's keeping me honest, all right. So we're kind of left, if we want to think about SPDEs, we're left with the first basic question. When is it that PX sometimes is equivalent, or even just one of them is absolute with respect to PX tilde? And so here's 3 infinite dimensional examples that I just chose. So I'm only thinking about kind of dissipative PDEs, ones that have like Laplacians. If you want to talk about hyperbolic PDEs or other things like that, that's a different conversation. Right? If you want to talk about Hamilton-Jacobi's, that's a different conversation. It's not singularly different, no pun intended. Actually, a little bit of pun intended. But this is what I have the most to say about in a coherent way today. Okay. So maybe it's worth just reminding what happens in finite dimension. So this is like a stuffed slide with way too much going on. So let me just actually leave this like this for a second. So in finite dimensions, if I have some SDE, right, then I have if I define U to be the density, so these are actually solutions, but now unfortunately I called U the solution of the form of Burkhoff equation. So I'm setting U x of t equal to this expected value. Then it's very well known that that solves a deterministic PDE, which is called the backward Kolmogorov equation. And its adjoint equation gives rise to this rho t, this transition density, which is the forward Kolmogorov equation or the Volcker-Blanc equation it satisfies. And if things are elliptic, then we know that such a density exists, that we have a nice density with respect to xt. That is to say, when I say elliptic here, I mean that this set of directions that I'm forcing spans all of the space. So in other words, there's the quadratic form, which is formed by taking the directions I'm forcing in, testing them against the direction, that's the inner product, that angle bracket for me, squaring it. That quadratic form A, right, that's clearly demonstratively a quadratic form, yeah? And that quadratic form A, which I just defined, is bounded below by the identity. It's non-singular. Which another way of saying that in finite dimensions is whenever C is equal to 0, whenever A of C is equal to 0, then C is equal to 0, right? And then of course, there's a slightly more sophisticated theory, which is that, well, sometimes if you don't have all the directions directly forced to sigma, which is what I used here in the ellipticity, you can get a hypoelliptic theorem where these directions interact with the nonlinearity, the lower order part of the symbol, if you're a PD person, right? The leading order part of the symbol interacts with this lower order part of the symbol, and this A and this A are different. Interact with lower parts of the symbol, and so you can create this kind of ladder, right? This filtration on a Lie algebra, increasing filtration, where you first look at the directions. So I take sigma k, I look at the vector field, the transport in that direction, which is yk, and I look at the span of that, and I just said, well, what if it's not everything? Then I let it interact with the nonlinearity. This is a Lie bracket commutator of vector fields. You act with this vector field on this vector field and this vector field on that vector, and you look at the difference, or maybe the sign reverse of that. And our left-handed planet, I actually live in a dyslexic planet, so I have no idea at any given moment, right? So for some n star, Victor's laughing, he's taken too many classes from me. He knows exactly what I'm talking about. So for some n star, if the dimension of this is full dimension, then we get again a density just like this. And what we just saw is that when we have a density like this, that it has points of positivity and y that agree, then we can perform a similar decomposition we did before. And that's why the phenomena of unique ergodicity for SPDEs in finite dimension in a way is much simpler. And there's phenomena that we don't see in infinite dimensions in finite dimensions that we see only in infinite dimensions. And that's what part of this conversation is to try to tell you about. Yeah, please, Isabel.
Do you see on the density that your equation is elliptic or hypoelliptic? Or are there different properties on the density?
Yeah, there are different properties. In
Like
particular,
what?
how it approaches, if it's elliptic, as you know, at least as well as I do, as you go back to time 0, it blows up like 1 over square root t. Of course, if it's hypoelliptic, the rate of that blow up, right, depends on the Theodori distance on the Lie algebra induced by that filtration, and you get a 1 over t, but in different directions. It actually, it's not, you get a lower bound, but you actually get fundamentally that it has in different directions, it blows up differently.
Okay, so it's the decay of your row in some sense.
What? Sorry, I didn't
Is
understand.
it the decay of the density row on the diagonal or something?
Yeah.
That tells you.
Yeah.
Okay.
Sorry, in what sense are you saying you fix the relevant topology in finite dimensions under ellipticity, second line?
Finite dimensions, it really, okay, this, I mean, more of a statement. In finite dimensions, there's only kind of one topology, right? There's kind of the topology of Borel open sets. Right? That's what happens. The problem is in infinite dimensions, there are many Borel open sets, many families of Borel open sets because all norms are not equivalent, right? And that gives rise to all of our problems in some sense. All right, so let me just maybe say, let's see, how long do I have? Okay, so I have 20 after or 25 after. So let me just go ahead and say a few things. So in general, so in some sense, this property of kind of having a density and having transition densities like this that are equivalent is very much, I think of it as a very finite dimensional property. So that you can have this happen in infinite dimensions, but it means in some sense you've made many parts of this infinite dimensional system, they're acting more finite dimensional, right? You've given this kind of this decay at infinity to be, well, you know, I'll get to that in a second. So let me look at these three examples. So these three examples each have different kind of sets of properties in infinite dimensions. So they each illustrate different things. If you think about these, so each of these I'm thinking in the simplest setting. I'm thinking of, you know, zero boundary, periodic boundary conditions, mean zero flow, or S1 with like this, or zero boundary conditions. So simple settings. And let's say these EKs are always the Fourier basis, the appropriate Fourier basis given my boundary conditions. Okay. I think about these EK, if I think about these sigma Ks here, if I think about these sigma Ks like example, let's think about sigma K equal to 1 over K to the P. P may be large. Okay. If you do that for each of these three examples, then it's actually true. It's actually true that they all satisfy this property. What it does is the noise obliterates the kind of the structure that each of these equations give out is something that's analytic. It's kind of Gevrey often, right? So it's much smoother than the forcing. So the forcing obliterates the fine scale structure of the nonlinear term in these equations if you decay like this. That's where when people first started doing SPDEs, that was what was kind of the best, that was where we started. It's a reasonable place to start. A lot of great and deep work was done. And in that setting, even these three examples actually have some interesting properties. So which I'll come up to right after lunch, right after the next break, is that this first example, if you start from two, so you notice here I'm asking for the absolute continuity at time t, right? So just at time t. In this example, you can actually make it so that not only are they equivalent at time t, but the measure they induce after on the infinite future path space are actually equivalent, starting from different initial conditions. Okay. Sorry, actually, let me say that differently. Okay, actually, sorry, roll that back. I misspoke. That was incorrect. Roll that back. This is what I want to say. So you can then talk about whether, so then what happens as I move up. So I told you that this is true, but you might ask, well, is this, before I had Lebesgue measure, could I write this as some density with respect to some nice measure that I know about on my infinite dimensional space? For the bottom two ones, you can actually write a Gaussian measure and show that it's absolutely continuous in many cases. So these transition densities are actually absolutely continuous with respect to some Gaussian measure. For this one, we don't know that that's true. And actually, I suspect strongly that I suspect strongly that it's absolutely continuous with respect to some Gaussian measure. It's something I'm thinking about. It's an open question. But we can also show that I suspect it's not absolutely continuous with respect to the obvious candidate. So in this example, in Burgers, if you force it with forcing like this, if I erase this nonlinear term here, then I get a Gaussian measure. This is just an OU process, a Gaussian process. And so if I erase this term there, then you can show that for big enough P, this is absolutely continuous with respect to the measure, the Gaussian measure you get by erasing that. For the reaction to fusion, you actually get that if you erase the nonlinear, you get that these are absolutely continuous actually on path space. And they're actually equivalent on path space. Burgers is such that you only get this absolutely continuous at a fixed time. Now, of course, things get more complicated. If we now start letting this P get smaller and smaller and eventually even become negative, flip up, right, and have very rough forcing, then we're into the realm of kind of singular Pde theory, right? So it's the work that some of the work of old quantum field theory and de Prato and de Buch and the big breakthroughs of Martin Herrer and Max Gubinelli, right? And so, we can then see what happens here. And so then it actually becomes more complicated here. And Jean-Christophe and some people have some nice papers where they talk about when these are singular, I think. Definitely various people have papers about that. But what's actually interesting, what I'm going to explain to you at the very end of next lecture, which maybe at this moment seems ambitious, I'm going to tell you that we can actually prove that the time t transition density of this problem is absolutely continuous with respect to the Gaussian measure for all p less than -1. And -1 is exactly when you're at the KPZ endpoint, okay? And so I'll show you, we don't know what's true at the KPZ endpoint, but I will stop there for a moment.
Thank you very much. Any more question?
I guess you just spent some time.
Hi.
Yeah, I guess you just spent like a bunch of time talking about like the literal way in which you inject noise into the equation.
Sound like you want your money back.
Yeah, kind of like affects the solution. Like other,
A lot of time spent about how noise is injected.
yeah,
Yeah.
like do people who do SPDEs think about like other ways to inject noise into the system at all, or like is it just like basis of L2 times noise? Like,
Usually is a very dangerous word in mathematics.
yeah,
Okay, people definitely think about that, what you just said. There are also people that think about multiplicative noise. In particular, you could think about forcing it in the direction of the appropriate direction of the vector of the drift field of the drift field. Sometimes people call that Lagrangian noise, because they're hitting it. It's like it's a limit as if you're hitting a certain particle. But as you know, there are other ways to inject randomness, and also I'll talk about that maybe at the very end.
Any other question?
So for these examples, do we know like global existence, like for all times, then we can apply like at least for like.
Well, I mean, I haven't told you anything about the sigma case. You certainly pick sigma case where you do and sigma case where you don't. So I am not going to belabor global existence uniqueness. Right? Just it'd be too long of a course if I did a separate course on kind of how to do standard Pde theory on SPDs, right? But in these three examples, I mean, if this looks like Laplacian to the alpha, we have then alpha equals 1 is equivalent to KPZ. So we have this all the way up to alpha equals 1. But in some sense, what's maybe more interesting is here to have minus negative k to the p, right? That's just as interesting. So this is one thing to, so this is a conversation about ergodic theory. So when you force it rough, you get like extra points from the existence of uniqueness part of the crowd. They all clap really loud. Oh, rough. Okay, but if you do that, the ergodic theory becomes easier. It becomes really easy, relatively speaking. So there's just the only thing that's your only problem you have, the same difficulties you had to prove the existence of uniqueness. If you can make sense of all the objects in the equation, then you can probably still do the ergodic theory, okay? What's harder sometimes is when you have so little noise, it doesn't spread well. So in some sense, the super smooth forcing, spatially smooth forcing is harder from an ergodic theory point. It's not always. There are certainly examples where, I mean, we'll talk about them soon where it doesn't matter. But,
See questions on Zoom?
yeah, please. Oh, hi.
Hi.
How you?
So maybe I misunderstood something here. So for the burger example, you're
I talk louder. I can't hear you.
You cannot hear me?
When I used to go out dancing, I used to think there was so much space right next to the speakers. I thought it was such a
Can
great.
you hear me now?
Now.
Yeah, we hear you.
Okay.
So for the burger example, when you choose p equal to -1, like the white noise case,
Yeah.
and we know that on the torus, the invariant measure for the burgers, I mean, for fixed t, the log is a white noise, right?
Yeah. Wait. It's only lecture 1.
Right.
Yes, I'm going to talk about that.
I think that for the linear case, the law is not okay. You conjecture that it's not absolutely continuous with respect to
Which case?
for the burger.
Okay, so the first answer, this is what, after the break, this is what I'm going to talk about. But let me just go ahead and tell the answer. I conjecture the following. I can prove when alpha, when it's slightly smoother than burgers, than KPZ, I can prove it's absolutely continuous with respect to the linear part. All right. That's a paper.
Yes, I know that paper.
Of course, what's that? Of course, when it's exactly right, when it's exactly gradient here, when it's exactly gradient, and this is when that's what's right there, yeah. When it's exactly gradient there, then we know that the invariant measure is white noise, right? Now let me just change a finite number of these in some strange way. Now you don't know that it's white noise is invariant. So what I want to say is that I think that the scaling is critical in that case, and you get zero regularization effect, and that's why like Martin had to work so hard to get that limit, that endpoint to work well. It's not really an endpoint, but I think we'll see that it's an endpoint in a different sense. But I conjecture that the reason white noise is invariant is exactly because the level sets of the Gaussian measure and the level sets of the energy are the same. It's a geometric statement that when you force in a direction which is tangent to the level sets of the invariant measure, then it's invariant. It doesn't matter. You can force with it as rough as you want. Having it go, I could make it negative, and I could rig it up. I can make something that's such a rough thing that you might not even be able to prove global existence or even low short time existence, but that would still formally be an invariant measure because of this geometric property. But the minute you tweak that the tiniest bit and break that exact geometric property, I conjecture that at that limit point, it's not true anymore.
Okay.
But if you didn't understand that, come back after Keith, because that's what I'm about to talk about.
Yeah, let's get to the second one.
He read the cliff notes, so he couldn't resist. You're very welcome. Thanks for the questions as always.
Oh yeah, Jonathan, you can see another question on the screen.
What do you want to know, Leah? Will you say things about using multiplicative noise and their effects later in the lecture? I wasn't planning to. What do you want to know, Leah?
Whatever you know about it.
Are you thinking about Wright-Fisher diffusions by chance?
Yeah, I'm not, I
Okay.
don't usually add more, noise independently like you do. So I'm curious what happens if you.
Yeah, so a lot of these theorems, there have been advances where you can apply similar theorems and get results in the multiplicative noise case. Martin has a paper. Some other people have some papers. I don't think it's, I think that the same issues that I'm talking about in the additive noise are the same in the multiplicative noise, but you have all the standard extra issues that you have in multiplicative noise in finite dimensions, right? About points being reachable and places with where the densities vanish and things like that, and trapping points, right? Like McKean-Feller theory of singular points, right? So I'm not planning to say anything about the short answer is I wasn't planning to say anything about multiplicative noise, but I'm happy to talk with you about it, Leah, later, or anyone who wants to ask me about it.
Okay, thanks.
Okay, let's thank Jonathan again.